So we have the list with firms and comms and which are the differences. Permutations, order matters. Order matters. So if it says the word arranging or arrangements, that's a huge thing that it's a permutation. And right now I'm just giving you a list of permutations and combinations, but they're not going to make a huge amount of sense until about Friday probably, which is which, because then we'll have learned combinations and then we get to pick between the two, okay? So right now we have a list, but they'll make more sense later. So where do places where order matter? Well, the things that you pick, you have to decide if the things I pick, if they were in a different order, would it change the outcome? If the things I choose, if they were in a different order, it would change the outcome, then it's a permutation, order matters. If the things I pick, if I change the order of those things, the outcome would be the same, then it's a combination. The order doesn't matter. So I'll give you an easier example. So say I had this class and I was saying that you guys could go on a class trip, 3 of you, okay? You're all going to the same destination, the 3 people I pick. Does it matter if you're picked first, second, or third then? Does it make you get a different experience? No. You get to go to the same place, so then it would be combination. Because the 3 people that were picked, if I flipped the order around, it wouldn't change what they got to do. Okay? But what if I picked 3 people to go on a trip, and one of you got to go to Edmonton, one got to go to Hawaii, and the other one got to go to Europe? Would the order matter in which those 3 were picked? Would it change if I changed them? Yeah, they get to go to different places, correct? So then the order of those 3 people matters, it would be a permutation. Okay? Those are the ones that people get a little bit more mixed up. If I was picking people for a group, so say I picked a subcommittee of the people who were on student council, and of that subcommittee, I wanted to make a new little committee, right? And I wanted to pick a president, a vice president, and a treasurer for that committee. Would the 3 ways you pick those people matter? Yes, they have specific jobs. But what if I was just picking a subcommittee from the big committee, and I just wanted a subcommittee of 3 people, and they were either on the committee or they weren't? Would the order I picked those 3 matter? No, it'd be a combination, because they're either just get to go on the committee or they don't. So if you're given specific jobs or positions, it's a permutation. Itineraries are permutations, so if you have to go in a certain order to somewhere, right? People sitting around, or if you're lining people up, if you're arranging people, if you're arranging books, if you're lining up cars, any of that stuff, it's a permutation because order matters. You're putting them in a specific spot, right? And if I move them to a different spot, it looks different. PIN numbers, codes, license plates. Actually, a combination lock should be called a permutation lock because the order in which you put the number in matters. I don't know why they call this a combination lock. It's actually a permutation because if you put the 3 numbers into your combination lock differently, you're not getting in, right? Phone numbers, permutation. Words are always a permutation because food and dofo are not the same word, right? So words are always permutation. Combinations are groups of people where their titles are not given, so they get to be on the group, in the group or not. So another one that messes people up is if you have like principals and you're choosing a subcommittee of principals, teachers, a subcommittee of teachers, or like you're going on a trip and a certain number of teachers get to go and a certain number of students get to go, right? So you're choosing teachers from teachers and students from students. So does the order matter? They either get to go on the trip or they don't. So does the order matter? No. So if you're pulling teachers from teachers and students from students, it's a combination, unless the people you're pulling from there have specific positions. Card hands are always combinations because I don't even know a card game, but maybe there's one in the world that's like this, where when you're dealt cards, you have to play them in the exact order you're dealt them. There would be no brain power needed, right? You would get the cards and then you'd have to lay them and you'd just be sad. The only one I can think of that's like that is like war, right? War, you'd have to lay them in the specific position. But if you're ever dealt a card hand, the moment you get cards in your hand, what do you start doing? Rearranging them. So does the order matter that you got them? No, either you get those 5 cards in your hand or they're not in your hand, right? So if they're in your hand or they're not in your hand, you go on the trip or you don't go on the trip, you're part of the subcommittee or you're not part of the subcommittee, then it's just a combination. The order doesn't matter because if you can move them around and it doesn't change it, then it's a combination. Pizza toppings. Although it'd be really disgusting if you started with cheese first and put the crust on the top, you still get the same cheese pizza. Not really, but you do. If you're dressing someone and they get to pick socks and they get to pick a pair of pants and they get to pick a shirt, does it matter if you pick socks first, pants, then a shirt? No. You're still making an outfit, so it'd be a combination. If you're making chili and you were throwing everything together in one thing, kind of gross because you wouldn't cook the meat first, but whatever. You could do that. You'd still have chili. So it'd be a combination, right? If you were picking an appetizer, a main course, and a dessert, would it be a combination or a permutation? Would you have the same meal whether you picked them in a different order? Yeah, it's just weird to us because of the way we are culturalized that we would eat our dessert last. But technically, if I ate my dessert first, my appetizer next, and my main course at the end, do I still have the same food in my stomach? Yes, so it's a combination. Order doesn't matter. All right, so those are the different things like that. Okay, so there's this thing called the fundamental counting principle. The fundamental counting principle is just a way to help us find out the ways that something can happen. It's not used for only permutations or only combinations. It can be used for particular cases. Could be perms or comps. So we're going to decide as well when we're going along if they're a permutation or a combination. So if you have a task made up of several stages, for example, you're building a wooden toy, which is what we're going to do, and there's a top, and there's a middle, and there's a bottom. We can use the fundamental counting principle because we can take the different number of tops, times it by the different number of middles, times it by the different number of options of bottoms, and we get all the different types of outcomes of toy we could get. That's what the fundamental counting principle states. If the number of the choice for the first stage is A, and the second stage is B, and the third stage is C, then we can multiply them all. Okay? Why is that? Because you need the top part and the middle part and the bottom part. The moment we use the word and, we are going to multiply. This is important. This is when you know whether you should multiply or add. And whenever we use the word or, we add. And add, we'll start with A's and with D's. They look like they should go together. They do not. If you use the word and, you multiply. If you use the word or, you add. So if I have 3 parts of a toy, I need the top and the middle and the bottom. So I'm going to multiply. That's why the fundamental counting principle multiplies. Because you're not going to have the top or the middle or the bottom. Because then you could have a toy with a top or a middle or a bottom. And is that the full toy? No. So I need and. I need to multiply them. So let's look at this example. A toy manufacturer makes a wooden toy in 3 parts. Part 1. So we have 3 parts to make this toy. Part 1 is the top part, and it contains red, white, blue, pink. Part 2 is the middle part, and it can be orange, purple, or black. Those are the options for it. Part 3 is the bottom part, and it can be yellow or green. So I'm going to show you in a tree diagram how we can represent all the different outcomes so that you trust that the fundamental counting principle actually works. You don't just trust me, you can see why it works. Okay? So we're going to start with part 1 at the top here. What I'm going to tell you to do is leave a space between all the colors, because off of every color we're going to get branches. And if we shove those colors tight together, you're not going to have any room to branch off of them. Okay? So we're going to leave spaces, so do as I do. So part 1 can be red, or it can be white, or it can be blue, or it can be pink. I leave spaces. So that's part 1. So if I only had 1 part to this toy, what would the possible outcomes be? A red toy, or a white toy, or a blue toy, or a pink toy. So I'd have 4 possible toys I could make, correct? So, but this toy actually has another part to it, so it's part 2. So if I have a red top, I could have an orange, purple, or black middle. If I have a white top, I could have an orange, purple, or black middle. Orange, purple, or black. Orange, purple, black. So if this toy only had 2 parts, a part 1 and a part 2, how many possible different toys could I have made? If this toy only had 2 parts, how many different toys could I have made? 12. If you have a red with an orange, a red with a purple, a red with a black, a white with an orange, white with purple, white with a black, that's 6. 3 more, 3 more. Yeah, we could have 6 toys, correct? What did we actually do? We did 4 times 3, did we not? And that's how many? 12 toys. It's the same thing. Why is this sometimes better than just going 4 times 3 and getting 12 different toys instead of showing it this way? Why would this possibly be better in some cases? If I go 4 times 3, I just know I have 12 different toys. Do I know what the different toys look like at all? No. This actually lists every single different toy we could have, right? So in 30-2, not in this class, but in 30-2, we deal with probability. So if they asked how many toys had a red top, well, you would say 3 out of 12. So this would be better for a probability question. We just don't have probability. So often tree diagrams for us is not better. Okay, I'm just doing it to prove a point. Then we have part 3. We could have a red top, orange middle, or a yellow or green bottom. So off of each of these, I'm going to have yellow or green. So now because I have a third part on this toy, how many different toys do I have? I went from having 12 toys to having 24. 12 to 24 is multiplying by 2, and I have 2 more outcomes that I added to it, right? So here I have 4 options times, because I need this part and this part and this part I'm going to multiply. So I have 4 options times 3 options. Oh, I did this in blue. I should do it in green. Times 2. And it's 24 different wooden toys. So this is actually the fundamental counting principle using those. And we always want to write statements because we want them to know that what we actually found and what it is, right? So if I just put 24, who knows what 24 is? I want you to write 24 different wooden toys so that I know that you know what you're doing and what you actually found. A lot of you just find math and then you get an answer and you box it, but you actually have no idea what it is. But you're like, it's right. That's all I know. I actually don't know what I found. So that's not a good thing, right? Because there's a lot of explains on your diplomas. Or compare, which means state the similarities and differences. Okay, I'm going to get you to flip ahead for a second to the 3rd page, to the questions to try. We're going to come back after again. I want you to try this question here. I want you to do it just the same as we did. That toy was a combination because the order doesn't matter which you picked, the bottom, the top, or the middle. You'd still get the same wooden toy, right? Here we have a football team has the following kit: a jersey that's red or black, pants that are white, red, or black, socks that are red or white. The team plays in a different uniform each week until it has to repeat a previous uniform. This is not true. You don't just like randomly pull pieces to make different types, but it's a really good question. Okay. Determine how many weeks the team can play before repeating the previous uniform. All right. So they want to know how many different outfits you can make with those options. So what I want you to do is I want you to use the fundamental counting principle, and I want you to show using the tree diagram that you can do it with a tree diagram too. This will be the only time I will ask you to do a tree diagram, just so you know, but I want you to be able to do it. Why are tree diagrams kind of sucky? If the outcome has 1,000 outcomes, you're not doing a tree diagram. Like you don't have enough time. Okay? So try this out. So here, I'm going to skip that for now. We're going to go to example 3. A Math 30 quiz, and if you're intending on using fundamental counting principle, you have to remember that you're going to put blanks for every single part of something, right? So when we did the toy, we put a blank for each different part of the toy. When you guys did the outfits, you did a blank for each type, like the jersey, the pants, the socks, right? All the different parts get a blank. So if you did a word, let's say, the first letter would get a blank, the second letter would get a blank, because those are all the different parts of the word that make the whole, correct? If you were arranging books on a shelf, say you were arranging 20 books on a shelf, how many different parts would make up the whole arrangement? If you're doing 20 books on a shelf, 20. So you'd have 20 blanks, right? For each spot, to hold a spot for each book, correct? Okay, so this one, we have a Math 30 quiz, consists of 8 multiple choice questions. How many parts are to this test? How many parts are to this test? I don't mean like multiple choice, numeric response, written response. If I had to write this test, how many questions would you say it had on it? 8. Thank you. Yes. 8. It totally would. I stopped right after 8 as well, so it's kind of giving you whatever. So this thing has 8 questions on the test. Do you have an option of doing 1, 2, 3, 4, 5, 6, 7, 8, or do you have to do all 8 when you write a test? All 8. I've yet to meet a teacher who's like, if you want to do 1, none, up to you. All that's for you. You have to do them all. So you have to do question 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8. I'm getting more steps on my Fitbit, just so you know. That's what I'm doing right now. So you get 8 steps. 8 steps. No, 8 steps. Okay. You have 8 blanks. I don't know what should say. That did not correlate. Like 8 parts to the question. I don't even know how I got. Oh, the da-da-da and the da-da-da. I got it. Okay. 1, 2, 3, 4, 5, 6, 7, 8, and we need them all. So we're going to multiply. We don't have options to not multiply. If we could only write 1 or 2 of the questions, it'd be an or. That's not going to happen. Each question has 4 choices, A, B, C, or D. How many different answer sets are possible? So we have A, B, C, D. I always list my options underneath, and then how many there are above. So actually, every single one of these would have 4, correct? So I'd have 4 options for this one. 4, 4, 4, 4, 4, 4, 4. People want to tell me that's 4 times 8. 4 times 8, you guys, is actually taking 4 and adding it 8 times. That's what 4 times 8 is. You make little groups, 8 groups of 4, and then you'd add up all the dots. That's what you did when you were little, right? So this is not 8 times 4. This is what? Yeah. Yes, 4 to the power of 8, which is substantially larger. I think it's 15,625. Oh, one of these answers later on is 16,525. 15,625. You wait, it'll be here. So what is it? I was out to lunch. So just a little bit more than what I said, just a tiny bit. So if you think, hey, I got 8 multiple choice questions, there's a good chance I'm going to guess them all right. Like I'm going to do real well. There are 65,538 different answer keys to an 8-question multiple choice. 65,538. So you have a 1 in 65,538 chance of guess. I would study. That's all I've learned from this. Study. Just guessing it, no, not pretty, right? Not going to happen. Okay. So what happens if I had restricted it, if I had said, okay, I know for sure I cheated, and I kind of looked at the teacher's answer sheet, and I know for sure that 1 was A and 7 was D. How would this change? Yeah. No, I get what you're saying, but no. I'm saying that 1 has to be A, not repeating, that's not, 1 has to be A, and 7 has to be D. Yeah. Nope, plus is not correct. You're doing right math, not correct. What would this be? How many options would I have for number 1? 1, A. How many options would I have for this one? 1, it would have to be a D, correct? So it would be 4 to the power of 6 times 1, because it'd be 1 times 1, which is 1. You could cross them off and luckily get the same answer. I would not suggest you doing that on the diploma, because then what the person who is marking you is thinking that those questions are going away, when those questions aren't going away at all. Like if you're going to show your work, if you just cross them off, you're saying, hey, question 1 and question 7 don't matter anymore. They do. There's only just one option and one option. So you'd still end up with the same answer, but I would hazard that they're probably going to take marks off your answer. Okay. So this is where we're at with restrictions. So if we have restrictions like that, I restricted the first one can only be A and the 7th one could only be D. You have to deal with restrictions first. It's written right here. The restriction is dealt with first. So we're going to look at number 4. In how many ways can 5 different models of black cars? The key thing here is different. If they were the same, which is going to be repetition, which we're going to deal with not today, but tomorrow. If they're the same, then I could put all 5 black cars in a row, and I could rearrange them and put them back, and you'd be like, nothing changed, right? If they were exact same 5 black cars, I could rearrange them a whole bunch of times, but they would never look different, correct? But if I have 5 black cars sitting in a row, and one's a Honda Civic, and one is a Toyota Tercel, and the other one is a Porsche, and they're perfectly the exact same black. If I move them around, you're like, they've been moved. That's great, they're the same color, but it's blatantly obvious that they're different. So if they're different models, putting them, I'd have to take the 5 arrangements into account, right? Which is good. So there are 5 black, and they're all different. And there are 4 different models of red. And they have to be parked next to each other in a parking garage. So that means all of them are being parked. How many cars are there? How many cars are there? 9. So how many parking spots are we filling up? 9. Each of them makes a part to the whole parking, correct? So we're going to put 9 spaces. This way we're actually visualizing what the parking lot would look like, correct? So it says here, if a black car has to be first, so I'm going to go here, a black car has to sit here, and a red car has to be last. So a red car has to sit here. I must deal with my restrictions first. So how many can go in the black spot? How many different options do I have to park? How many cars options? Yeah, 5. When I was in high school, I was an idiot. I was like, okay, we parked 5 there. So now I have 4 left. I was like, what am I, stacking them? Like, I think now, like, how stupid were you, Crystal? Like, you were just a dumb, dumb, dumb person. And now I'm your teacher. You're welcome. Okay, so 1 parking spot, room, park, 1 car. Don't stack all 5 on top of each other. That's ridiculous. You just ruined the 4 underneath. Okay, so you have left 1 car there. Stupid teenage Crystal left 5. Don't leave 5 there. That makes no sense. So I left 1 car there. Yes? Okay, then we go to the red. How many options do we have for this? 4. Remember that on top of the blanks are the number of options that you have, not the amount of cars you are parking there. Because now I was like, well, all 9 parked. What do I put in the blanks? And then I would leave them blank. Like, stupid. Seriously. And you're probably like, some of you are like, I don't get it. That's what I'm doing right now. And I don't, if you're that person, just hold it in, because in a few seconds it'll make sense. Okay, so I have 5 options for here. I park a car, room. 4 options here. I park a car here, room. How many cars are parked? 2. How many are left? 7. You guys are not nearly as dumb as I was. I was really stupid. I was like, all parked, done. 4 times 5, 20. I was bad. Okay, so what's here? 7. And then 6. and then I park a car. 5, and then I park a car. Then I park a car, then I park a car, and then I have just the last little car. Now, are we parking all the cars? Like, are all the cars parked? Yes, so I need to park this car, and 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 this car. So I'm going to, and means to, no, and add sound like they should be together, but they're not. They're haters. They hate each other. Thank you. Multiply. Haters gonna hate. So are ands and adds. They're gonna hate. Okay. Now, we could go 5 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 4. Fine. But there's this little button on your calculator. It's a factorial symbol that represents when I take a number and I multiply all the way down to 1. So in this case, I have 7 times 6 times 5 times 4 times 3 times 2 times 1. My calculator will do that if I just type in 7 factorial. It's not a 7 screaming. It's the factorial symbol in math, okay? That was funny. It's an exclamation mark. It means you're screaming or loud. Right. So then I have left 5 times 4, correct? And 5 times 4 is 20. So I can go 7 factorial times 20 and get my answer. Where is that lovely factorial symbol? You're going to go 7. And then you're going to go math. And then you're going to arrow to the left, and it pops you onto probability. So you have to get the probability somehow in number 4. Or left or right or whatever. Get yourself to probability, number 4. Hit enter. And then times that by 20. Yes. And what do you get? And if this was a written response, I wouldn't just say 100,800. I'd say 100,800 ways to park 9 different cars in a parking garage if a black car has to be first and a red car has to be last. I would just reiterate that question. Boom, done, drop the mic. I know I did it right. Yes? Because you could have went 7 factorial times 5 times 4 and you would have still got the same answer, but I was being lazy and I went 5 times 4 is 20 and then there's times by 20. All right. Now, how can you tell if something is odd? It's not weird. How can you tell if a number is odd? Sorry, I shouldn't say something's odd because that doesn't make any sense. Most people say it's divisible by 2, which is true. But how can you look at a number and tell me if it's odd? So I'm going to say 24. Odd or even? Even. 27. 23. 21. 28. 26. 20. What am I changing? The last digit. That's it. Right? So now I give you 7,653,542. Even or odd? Even. You don't give a hoot what I'm saying before this. You just care what the last number is. The last number was a 2. It's even. Right? So if something says it's odd, the last digit has to be 1, 3, 5, 7, or 9. We agree? Now, it's also going to talk about digit numbers. So in this case, it's going to say 4-digit number, and we'll read the question in a second. But say I told you I was going to pay you in a 4-digit number, okay? So I said, I'm going to pay you in a 4-digit number because I'm really cool like that. So I'm paying you $657. You're like, that's not a 4-digit number. That is a 3-digit number. I'm like, okay. I said I'd pay you in a 4-digit number. So I'm going to pay you. Perfect. And you're like, no, you idiot. That's a 3-digit number with a 0 in front of it. So when it says 4-digit number, what are they indirectly telling you? What about the first digit? Can't be 0. So they're not going to say, I want a 4-digit odd number where the first digit cannot be 0. Would that be nice? Yes. They're not going to. They're going to say, I want a 4-digit odd number. What does that mean? I need, my first digit can't be a 0 because it's 4 digits, right? And my last digit has to be odd. Now, if they say 4-digit code, can it start with a 0? Can a code start with a 0? Yes. So you have to watch. If it says 4-digit number, it can't start with a 0. Sometimes you'll see 4-digit code, and then people are like, it can't start with a 0. Well, codes can start with a 0. Code could be all zeros, right? So it's a 4-digit number. So let's look at this question. It said, Eric has been assigned the task of determining how many odd 4-digit numbers there are. And then it says, he has been told that a number such as 5267 is a 4-digit number, whereas 0267 is classified as a 3-digit. They will never tell you this on the diploma, ever. They're not going to tell you that. They're just going to say the first sentence. Eric has been assigned the task of determining how many odd 4-digit numbers there are. So how many parts make up this, how many digits make up this number? 4, so I need 4 blanks. Does it say anywhere in here that I can't repeat the numbers, like 000 or 111 or 732, 732, 7322? Didn't even repeat anything there. Does it say anywhere in here that they can't repeat? No. So you assume you can. The only time you cannot repeat is if it says you cannot repeat. They're not going to say, and you can repeat. They're just not going to say you can't. Okay? So if they don't tell you can't repeat, you assume you can. All right. We have to start off with the restrictions first. So this one back here has to be a 1, 3, 5, 7, or 9. This one up here just can't be a 0. We agree? We have to deal with those first. So the back one is a 1, 3, 5, 7, or 9. How many options is that? 5. This one can't be a 0, so it can be the digits 1 to 9. How many options is that? 9. Worst case scenario, you do it in your head and get it wrong. Use your fingers if you have to. 9. Okay? So it's 9. Is there any restrictions on the middle ones? So what numbers could they be? 0 to 9? Why can't it be the number 10 in the middle? Why is it 0 to 9? 10 is really just a 1 and a 0, right? It's a 2-digit number. You can't put 2 digits in a 1-digit blank. So that's why it's 0 to 9. So then dumb Crystal in high school was like, you just told me I can't put a 10 in the blank, and I'm putting a 10 in the blank. That is wrong. What dumb Crystal didn't realize is that we're putting the number of options on the top, right? Not what the actual number is. So my options are 0 to 9, which is actually 10 options. So that's why I'm putting a 10 up here. It's not the number 10 that's going in that blank, correct? That's the number of options that are in that blank. That was a hard thing for me. Does that make sense to you? I don't want you to be like I was. I want you to be better. Yeah. So 10, make sense? Okay. And then we need this digit and, so we're going to multiply. So we have 4,500 4-digit numbers that are odd, that can repeat. That's what we would write in here. In B, they trump it up. You've now been assigned the task of determining how many odd 4-digit numbers there are with no repeating digits. So same question, but no repetition. I wish I would have known how to do this properly in grade 12. I did not, but I have found a way that will work all the time. So we're still going to do the same thing. We have 1, 3, 5, 7, 9, and we can't have a 0 here. The only difference is we can't repeat. Okay? So what I'm going to do whenever it says I can't repeat, I'm going to hold a number somewhere. I'm going to box it, and I'm going to hold it there. Doesn't matter which one you pick, just pick one of them. So back here, I have 5 options. But now I'm going to pretend to keep one there because I can't repeat that same number again, correct? So I'm lazy, so I pick 1 or 9, so that when I have to write my options underneath my blank, I can just go like 2 to 9 or 1 to 8. If I pick like 4, I'm like 1 to 3, 5 to 9. Like, that's more work for me. I don't like that. So I'm going to pick a 9. And I'm going to box it, and I'm going to keep it there. Could you have picked any of the other 4? Yes, just pick one so that you're taking that option out. Okay, that option is now being used. So then in the first blank here, I have the options 1 to 8 now, because I've used up the 9 sitting there, right? So 1 to 8 is how many options? 8. Then I have to hold 1. So I'm going to hold the 1. And then I have 2 to 8. And people put a 7 all the time. And then they go 6, and then they put that answer, and then the answer is always there, and it's wrong, and it's picked more than the correct one. Why is it wrong? What am I forgetting? I'm missing an option here. What number could I use? Yeah. 0. The catch here is when it's odd, I didn't have an option of using a 0 back here, correct? When it was a 4-digit number, I didn't have the option of using a 0 here either. Have I used a 0 though? No. So in the second blank, I have to remember to bring that 0 back. So I actually have 8 options. I'm going to pretend to keep the 0. And I have 2 to 8, and I have 7 options. Does that make sense? If you're someone who wouldn't remember the 0, which I'm going to bet is almost not 100% of you, just from based on teaching this class a lot, leave yourself a little note. Say, don't forget to bring the 0 back when not repeating. Okay? Make sense? What's the answer to that? 8 times 8 times 7 times 5. Yeah. Does it make sense that I would have less than half if I take away repetitions? Yeah, 1, 1, 1, 1 would be out. 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4, 1, 1 something, 2, 2 something, right? 1, 1, 1 something. Those are all out. So it would make sense to have less than half. Okay, I'm going to get you guys to flip ahead to those questions we were working on. So I'm going to get you guys to try 2. 3, remember the answers are at the back. 3, the hint of 3 here is the score at the end of the second period of the hockey game is 6-3. Jerome was attempting to determine how many different possibilities there are for the score at the end of the first period. So they could have scored nothing in the second period, right? And they could have had 6-3, correct? So they could have 6-2, they could have 6-1. The catch here is you have to remember something. This, I'm going to give you a hint. Score can be 0-0. Just keep that in mind. So write that as a little hint. The score can be 0-0. This one? This one? And that one. Okay? So you basically have to have 1 to 6 done on questions to try.